So for the past few videos, we've been talking about the spin operators, which I said were the sigma x, sigma y, and sigma z. These are the Pauli matrices. Pauli matrices. And these are spin operators. And I've said before, these are things that we choose when we set up the experiment. We decide how to orient our instrument, and so that is choosing one of these. But there are operators that are things that we do not choose, and so we can maybe think of time as an operator, because time operating on your system like this will cause it to change into, so we'll call this psi 1, and that might change it into some other state, psi 2. If you just leave it alone for a while, it will change into some other state. And so we can think, well, is there something called a time operator? Well, technically there is no time operator. So we often talk about the time evolution operator, and we think of this like an operator, but that's essentially just to try and get rid of this time evolution operator for the thing that we can actually say is an operator. And the reason that time is not an operator is there's no Hermitian operator that gives you time as a eigenvalue. But we'll sort of pretend here with a time operator. So if we have a system, we'll call it A, and we'll say that is at some time t naught. If some time passes, so time passes, then we will say that is now some operator, which I'm going to use u here suggestively, and that is acting on the same ket here, on the same state. And so this is this operator acting on this state here is what happens to that state after some time passes. And so we can imagine that if no time passes, then U is going to be equal to the identity matrix, because the identity matrix multiplied, or the identity operator, I guess, operating on our state is just going to give us the same state back out. And so if no time is passing, then that's sort of obviously true. And so what I am going to do, so yeah, I will write it this way. So if we do have time pass, I will put A here, and T1 is going to be equal to our operator here, and I'm going to put that this is T1 and T0 acting on our system at T0. So our system at some time later is the operator here, the time evolution operator, acting on our system at some time t0, at some starting time. And so from this, what we can say is that the state A at t0 is equal to the sum. So if we do a linear combination here, so the sum over I of our probability amplitude here, which I will put as Ci, and we want to say that this is at time t0, acting on our system here. So this is our, well, these are the basis of our system. And so we can also say that that A at time t1, we can do a linear combination of that, and so that will be the sum over I of C I now at t1 rather than at t naught there, and that is acting on our system here. So AI. Okay, and so from this, what we can say is that it is not necessarily that any particular Ci at t naught is equal to Ci at t1. So for any given I, the probability amplitudes do not need to be equal to each other. However, it does need to be the case that the sum over I of Ci for t naught and squared, so that's the probability, is equal to the sum over Ci at t1 and that squared. So the probability for one and the probability for the other have to be equal to each other. And this is what we call the conservation of probability. So the total probability has to be equal for each of them, but these, because any particular probability amplitude is going to be changing. I mean, that's exactly what we're saying, is that the probability amplitude for the different bases in this is going to be different from this because we've acted on it with this operator here. And so from that we can also state that if we do the inner product here of A at time t naught with A at time t naught, then this is going to be equal to, so the probability, as we said, has to be equal. That's what we established here. So the inner product would have to be equal to A at time t1 inner product with A at time t1. And this would be equal to A at time t naught multiplied by, so this is a bra, so when we act on it with an operator, we also have to take the complex conjugate and transpose of that, which we use this dagger here, and we will call this T1 and T naught, and then we're also multiplying by the ket, so we have to multiply once again by this T1 and T naught, and then that is acting on our ket here, T naught. And so for this to be true, excuse me, then this has to be equal to the identity matrix. And so this is this property here, multiplying the complex conjugate transpose by the matrix here, this is called unitary. This means that it is unitary, which is why I used U for this suggestively. So this is the unitary, and this is all to show that there is the conservation of probability, and so we have that property right there. And so the other property is what is called the composition property, and we will talk about that here. Well, that essentially means that if we have a state here at, we'll say, at time 1, so I'll keep using my t naught, we undergo some time here, so that we are now at time t1, and then we undergo some more time here, so that we end up at t2. So this right here would have to be the same. Well, if we had an operator operating on this to bring it to here, and then another operator operating on this to bring it to here, it's something that you could express in a single operator that is sort of a conjunction of the two operators. And so we will denote that as u t2 t naught, which is going right from here to here, is equal to u t2 t1 multiplied by u of t1 t naught. And so we're saying that going from here to here is the same as going from here to here and then here to here. I mean, when we go from here to here, we sort of pass through this state, but we're saying that we're saying that we're composing these. That's why it's called the composition property. And we can say then that that our t1 t naught here, we can call that u, and then we will call that t naught plus dt, so plus some small infinitesimal amount of time, and then t naught. So that's essentially like we're going from here, then just right to something infinitesimally close to it right there, and we will call this the t naught plus dt, and then t naught here. However, if we take the limit as dt approaches 0, then what we have again is the identity matrix, because that would be the same as having no time pass when dt approaches 0. So that makes this the identity matrix. And so we can sort of talk about if there is some dt that is non-zero, if it's very small, then we can talk about u as being, so we can talk about that as being something like, so u t naught plus dt t naught. We can call that, so the identity matrix, and then we always subtract here. I think that's just sort of convention. We subtract, and that will be subtracting I omega dt. And so omega is a Hermitian operator. So omega equals Hermitian operator. So this is an identity operator. This is a Hermitian operator for generating time evolution, and this is a frequency essentially. So it has units of 1 over t, and so I will just I will tell us that we need to get our units as energy. And so what we're going to do is multiply this by something that has joules times second. So we can call the time here seconds, 1 over seconds, so that we cancel these out and end up with joules. And I will just sort of, I'll explain this in just a little bit, but we will say that that what we need is, we need our omega to be equal to h bar, which is the modified Planck's constant, times this h here, which we will so we know that this here is joule times seconds here. So yeah, I screwed this up. It should be H over H bar because so this is still joules per joule times second here because then if we multiply it by this, which has the 1 over seconds, then our H, which we haven't really defined yet, will be in joules. So that will be in units of joules, which is energy. All right, so let's go back to what we had here. So we said that our U is equal to the identity matrix with some extremely small difference right here multiplied by this this matrix here. But now we can turn that into the identity matrix minus I H over H bar dt. And so this is still, I'm just going to write U just to make it easier to write. So U is equal to that. And so now if we want to do U multiplied by U dagger, which is the transpose and complex conjugate, that will be I minus I H over H bar dt multiplied by I plus I, because it's complex conjugated, H over H bar dt. So if we multiply this through I times I, so it's identity times identity, that's just the identity. The identity is essentially 1 in matrix form. So 1 times 1 is 1. So we have I. Then we have the I times this plus this times I, which is going to end up being, I'm going to kind of cut to the chase here, I dt. I'm actually going to change that to epsilon just so it doesn't have the d and the t there sort of confusing things, but we are saying that is equal to dt. It's just some really tiny amount of time. So that's what dt is, and that's what we'll say this this epsilon is. And that will be multiplied by h plus minus h. And so then it will also be minus, I'm not going to go through it, but it'll be something that has epsilon squared here. And we said this was really tiny. And so something really tiny multiplied by something really tiny is so small that we can just ignore that. And so we are saying that U times U dagger here is equal to this. Well, we've already said that U times U dagger is equal to the identity. So this here has to be 0. We know that this isn't 0, and so this must be 0. And that tells us that this is a Hermitian operator, because we know that if it's Hermitian, then H has to be equal to its transposed complex conjugate. So if we have H minus that, then that has to be equal to 0. So that is how we know that H is going to be Hermitian. And so I'm just going to tell us that this H is going to be the Hamiltonian operator. And the reason we can say this now, we would have to sort of cover a lot of classical mechanics. So we'd have to do Hamiltonian mechanics, which is part of classical mechanics. And what you will find with that is that that your Hamiltonian is the operator that that causes, well, it causes evolution in time. So the Hamiltonian is our real time operator. And we said up here that that this has units of joules. I don't remember if joules has an O in it or not, so I'll just put that there anyway. So if we went back to classical mechanics, uh, so the Hamiltonian is equal uh, to the sum over I of, so this qi here with the dot is velocity, and then we have pi here, that is the momentum, and then subtract the Lagrangian from it. And so L is equal to the kinetic energy minus the potential energy. And kinetic energy, we know, is 1/2 mv squared. So I always hate that they use v for potential energy, because then we have v for velocity as well. So this should be sort of an uppercase v, and this is a lowercase v here. And then, so what we can also tell is that that if we have velocity, so and the momentum here, so momentum is mv multiplied by v equals mv squared. So what we can say is that we have mv squared, and then we subtract 1/2 mv squared plus our big V here for the potential. And so this will be mv squared minus 1/2 mv squared. So what we end up getting there is 1/2 mv squared plus our potential energy. And that is equal to our Hamiltonian, because we got it from right here. So this is just, so if L, if the Lagrangian is kinetic minus potential, H is going to be equal to kinetic plus potential. And the potential is often something like the Coulomb's law, which you might see if we keep using this uppercase V, and we'll say that that is a function of r and t equal to k, which is just a constant, the first charge and the second charge, and then the distance between them. And we can say that this is a function of time, essentially saying that if we have a particle here and we have a particle here and this one's moving this way, then the r here is going to get shorter. So r at time 1 and r at time 2. And then it'll go back to being the same as at r time 1 when it gets there. So this is changing in time. And so this is often the potential that gets used. It's not necessarily the potential that gets used. There are a lot of different potentials, but if you're talking about an electron orbiting a proton, then this is what you would use, because this would be your electron and your proton and the distance between them. But anyway, this isn't a video on classical mechanics. And so we know that if we have our u here, which we will say is the t1 plus dt, and then t naught. And so this is going from t naught to t1, and then to some other time that's dt away from t1. Going from t naught to t1 doesn't necessarily have to be infinitesimal. And so we can express that this way is ut1 plus dt and t2 multiplied by u t1 t naught. And so we know that this, as we saw before, is equal to, so this one is equal to 1 minus I h, and I'll keep using the epsilon here, over h bar, and then we multiply that by this one, which, as we said, isn't necessarily infinitesimal, so we don't express it this way. So that is u t1 t naught. And so then we can distribute that u t1 t naught over this, and we end up with, so we're going to use this one here, so that's t1 plus dt, and then t naught is equal to u t1 t naught minus I h epsilon h bar u t1 t naught. And then we can subtract this from both sides, and what we end up with is u t1 plus dt t naught minus u t1 t naught equals minus I h epsilon over h bar multiplied by u t1 t naught. And so from here, what we can do is, well, we'll divide both sides by this epsilon here, by this epsilon, and we end up with this, which we can see is a change. So I probably should have put the states in here, so we could just multiply everything through by the states here, and this is the change in the state with the change in time. Remember, we said the epsilon was dt, so the form of this is going to be the same as if we had our partial derivative of u t1 t naught with respect to time is equal to negative I h over h bar u t1 t naught. And once again, we can still have our state in here, so I'll just keep putting the state in there. I mean, what I did here, it shouldn't matter that I didn't have the state in there, because at any time here we could have just multiplied everything, multiplied both sides by the ket vector. And so from there, what we end up with is, so now we can multiply both sides by h bar and divide both sides by minus I. So we end up with h bar over minus I multiplied by this delta u t1 t naught, and then our state here with respect to time, and then that is going to be equal to h acting on this unitary vector here, t1 t naught, and then psi, our state here. And since we know that since A, our state A, so if just any arbitrary state A with t naught t1, so the state of A at t1 after T naught. So we could even call that just delta T. We could call that A delta T if we wanted to, is equal to the UT1 T naught operating on A at T naught, at time T naught. So at time T1, it's this operator acting on the state at time T naught. And so what we can do is we can sort of substitute this in for our unitary matrices here and our states. And I'm going to fix this up too, so we can multiply that by I over I. So I times I is -1, and then negative makes it positive, and then we just have the I up there. So we have positive I H bar, our delta, and then we have, so we can have this, we can put it here as the delta T over dt, and that is equal to H, and then this with delta T, saying that the T1 minus T naught is equal to our delta T. And so we're already saying that this is changing over time, so we can just express this even more simply as IH delta, and yeah, I'll keep it in the ket vector. You will oftentimes see this not in the ket vector, but I'll just keep it there. Dt equals H, and then our state here. And so you may recognize this as what is called the time-dependent Schrodinger equation. Put a little umlaut there. Schrodinger equation. And I mean, this, I guess, is kind of a derivation of it. And in future videos, I will be going through a lot more of ways that we can come up with things like this. And so what we can tell from looking at this is we have this change in the state as a change in time, and that is equal to our Hamiltonian operator here. And so that's how we know, well, we just kind of showed that the Hamiltonian operator is the time operator, because the way our state changes over time is controlled, is dictated by the Hamiltonian operator. And I will give sort of a little sneak peek here. So the Hamiltonian operator, which I said before is defined in classical mechanics, is the kinetic energy plus the potential energy. And what we will see in future videos is that this is going to be H, so H bar squared over 2m multiplied by the second derivative with respect to position, so not time but position, and then plus our potential energy here, which will be a function of position and time here. And so this part here is the kinetic energy of our quantum system, and this is the potential energy. And as I said, the potential energy is oftentimes, so we can put this as V R T is equal to the Coulomb's law. So Q1, Q2 over R. Actually, I think I messed that up earlier. That should be R squared, and so we can say that that is a function of time. So yeah, that should be r squared. It's a inverse square law with the potential, with electric potential, and so yeah, we will see this more in the future, and we'll study what this is saying and how we get it and all that in the future. But I just wanted to sort of show how just assuming this sort of this time evolution operator, we can go from there uh, and we can get to the this time-dependent Schrodinger equation, which tells us that this Hamiltonian operator right here is telling this system how to change over time. And this h bar is just telling us that it is a quantum system. It's a constant that sort of tells us what sort of how large a change can be. So, I mean, the sort of fundamental idea of quantum mechanics, which oftentimes sort of goes unstated, is the idea that everything is quantized. So if you want to get from this state here to this state here, then you sort of instantaneously jump from here to here. There's no occupying this area in between, and the smallest that this can be is Planck's constant, which is, if I'm remembering off the top of my head, it's 6.626 times 10 to the negative 34, maybe, and then joule seconds, as we said earlier when I said that when we had that omega and we had that equal to the h over h bar, and I said that the h bar had joule times seconds as its units here, and so we know that that this has to be joules here, because if we multiply both sides by the h bar, this we know has the 1 over seconds, and then that gives us joules. So the difference between h and h bar, so h bar is equal to h over 2 pi, or oops, that's an h. I'm so used to writing h's all the time. 2 pi. And this is just often used because there are so many times where you end up with 2 pi's in your equations, and so scientists have just found it easier to just use this h bar. And you could even think of h bar, oops, now that I want to write an h, I couldn't. H bar as being in units of joule seconds per radian, because this 2 pi is a unit of radians. Yeah, and so that is a way you can think about it. So radians are usually said to be unitless, but if you want to think about it this way, it's joule seconds per radian. But the take-home message in all of this is just, like I said, we just sort of assumed this time evolution operator, that there is this thing that we have that when you operate on a state at time t naught, that you will have, that it will give you something different. So that will give you some state at time t1 in the future, and we said obviously if no time passes that u is going to equal the identity, because the identity times some state at t naught is just going to be that state at t naught, because no time has passed. And so sort of assuming that time evolution operator, we went through these calculations here. We saw that we conserved our probability, and so we saw that this had to be unitary right here. And then we did our composition here, so that we knew that we could break this up into two different times. So if we have an evolution from right here to here, we could also say that it's an evolution from here to here, and then from here to here, and that was what the composition was. And so we could use the composition for that. And then we said that at the limit where there is no change, we as that approaches, the change approaches zero, that we're at I, and so from that we could discern that if there is some tiny change here, that we could express that as the identity matrix minus some very, very small change here. Then we went through this and showed that that this H here, which we just sort of defined using this omega, essentially just using dimensional analysis here, and knowing that omega is a frequency, and we needed it to be in joules, in energy, that we needed to turn this omega into something that had energy up here and then joule times seconds down here for the units to work out. And like I said, from that we went through this and showed that this was Hermitian. I then said that that H was going to be called the Hamiltonian operator, and I showed sort of how that works in classical mechanics, with us ending up where H in general is equal to the kinetic energy plus the potential energy. And so we knew that that was what H had to be. And then we went through this where we split this up. We used the composition here, and then we used the composition right here, but we just substituted this in for this right here, and we multiplied it like this. Then we sort of distributed this into here, because we, well, I guess we don't know. I didn't mention it, but this is linear, if that matters to you. If you are a mathematically inclined person, then that will be important to you. But I just sort of assumed that throughout this. But anyway, we distributed it through there. From here, we just kind of did a little bit of algebra, and we ended up with this right here, which is that change in our state. So the states here, over some infinitesimal change in time, which we could then express as the partial derivative of the state with time, equal to this. From that we did just a little bit more algebra, essentially, and we substituted this in for this, and we ended up with the time-dependent Schrodinger equation. And so, yeah, that is what I wanted to talk about in this video. I hope you found that helpful, and I will see you in another video.